Welcome to the Explainer. So, today we're diving into what honestly looks like a total paradigm shift in how AI systems process the real world. For years now, the AI industry has leaned on this sort of Frankenstein approach to building vision language models. We've essentially been bolting new sensory organs onto AI brains that, at their core, were only ever meant to read text. But looking at this new architecture called InternVL3, well, it seems they are completely upending that playbook. They've built a natively multimodal system from scratch, and it's fundamentally changing what open-source AI can actually do.
Now, you might be wondering, why do AI models suddenly forget how to read when you teach them to see? I mean, it sounds completely ridiculous, right? But this is exactly what happens with a phenomenon known as catastrophic forgetting. Imagine you've spent your entire life doing nothing but mastering the dictionary, and suddenly someone superglues a pair of binoculars to your face and demands you describe a painting. You'd probably stumble over your words too. And that is literally what current open-source vision language models do. Let's see if we can figure out exactly why that happens and how this new paradigm is trying to fix it.
Okay, here's our roadmap for today. 1. The alignment debt trap. 2. The native pre-training solution. 3. Innovations under the hood. 4. Weighing the trade-offs. And 5. The unified future.
Section 1. The alignment debt trap.
Up until now, the default way to build a model that can see, think of models like Lava or QuenVL, has been this clunky three-step post-hoc process. You take this massive large language model that just spent its entire multi-million-dollar training budget solely on text. Then, you freeze its brain so it absolutely cannot change, and you awkwardly bolt a vision encoder right onto it. You're basically forcing a pure text brain to process visual tokens after the fact, and this creates what researchers are calling alignment debt. Because the base LLM was never designed to handle visual information natively, forcing it to do so creates severe, measurable technical friction.
In this debt, it causes real headaches for developers. First, we see catastrophic forgetting. The model actually gets dumber at text. We routinely see scores on standard math benchmarks like GSM-8K take a massive 5 to 10-point nosedive. Pure text reasoning agents literally regress. Second is answer drift. If you change just a tiny bit of phrasing in your question about an image, the model spits out wildly different answers, mostly because the vision tokens are so weakly bound to the text reasoning. Finally, visual text inconsistency. The model might perfectly describe an image of a red car, but when you explicitly ask what color is the car, it confidently hallucinates blue. The visual tokens just aren't integrated into the model's internal logic checks.
Section 2. The native pre-training solution.
Enter InternVL3, detailed in a fascinating April 2025 paper by Zhu and colleagues. It looks like they totally threw out the post-hoc approach. Instead, they execute one single pre-training run. Text, images, and video are all interleaved together from the very first computational step. In this architecture, visual tokens are treated as first-class citizens right out of the gate. There's no awkward unfreezing and realigning phase. The model simply learns to think in both text and vision simultaneously.
But to pull this off without racking up that alignment debt, you obviously can't just throw pure text at it anymore. Look at this exact data recipe. It's pretty wild. 40% of the training diet is pure text, which keeps its reasoning and language skills sharp. But a whopping 35% is interleaved image text data. Think of long documents or web pages where images and text just naturally flow together. Another 20% is direct image caption pairing, and the last 5% is video text data. This diverse, synchronized diet is absolutely the secret sauce to native understanding.
Section 3. Innovations under the hood.
Let's pop the hood and see how this builds a more efficient machine. One of the massive upgrades is how the model actually understands position and space. Previous models like QN used a fixed system for encoding positions, but InternVL3 uses something called V2PE, or Variable Visual Position Encoding. Think of it like this. Text needs one dimension. It's just a line of words. Images need 2 dimensions, like a grid. Videos need 3 dimensions, a grid moving through time. So instead of forcing a rigid grid on the model, V2PE allows it to flexibly allocate its processing power depending on whether it's looking at 1D text, 2D images, or 3D video. This elegant flexibility nets a clean 1 to 2 point gain on tough video benchmarks right out of the box.
Another huge leap in efficiency is the Visual Resolution Router, or VR. I like to think of this as a smart bouncer for the model. Normally, AI models just brute force every single image at maximum resolution, wasting huge amounts of compute. VR analyzes an incoming query, predicts the absolute minimum resolution needed to answer it, and routes it accordingly, from a low 256 tokens all the way up to 2048 plus.
So the crucial takeaway here is that for 60% of production traffic, low or medium resolution is plenty. A simple photo of a dog doesn't need to be analyzed at microscopic levels. This optimization alone stops the system from burning precious processing power on easy tasks.
And then we have deployment. When you run a massive model, the vision parts and the text parts actually choke on completely different hardware bottlenecks. Vision processing gets jammed up at the GPU's memory bandwidth, while text generation bottlenecks at the system's memory cache. InternVL3 solves this through DVD, or decoupled vision language deployment. It literally splits the vision encoder and the language model onto separate physical GPUs. The vision GPU processes the image once, streams the data over to the language GPU, and that one handles the text generation. It is honestly a stroke of architectural genius.
And the result of that decoupling? DVD roughly doubles the per-node throughput compared to a traditional co-located setup. You're getting twice the output simply by organizing the hardware to match the native architecture of the model.
Section 4. Weighing the trade-offs.
Now, despite all this incredible performance, we do need a quick reality check on the brutal costs of this paradigm shift. While native pre-training definitely kills alignment debt, the price tag is staggering. Looking at the compute cost, post-hoc training is relatively cheap because you're reusing a pre-trained LLM. Native pre-training, that demands millions of fresh GPU hours. Then there's data. Pure text is abundant. We have trillions of tokens. But interleaved image text corpora are incredibly scarce. Finally, upgradability. In a post-hoc setup, if a better text model drops, you just swap it in. With InternVL3, you can't. The vision and text are fundamentally fused. It is impossible to upgrade one without the other. Which means post-hoc training isn't going anywhere just yet for everyday developers.
So why are researchers willing to pay these massive costs? Well, look at the benchmark results. This single-stage recipe creates a generalist model that rivals the absolute best proprietary, closed-source models in the world. The 78 billion parameter version matches Google's Gemini 2.5 Pro on complex benchmarks. The 38 billion version matches OpenAI's GPT-4o, and the smaller 8 billion version is absolutely crushing the open-weight leaderboard for its size class. That right there is the payoff for taking the hard road.
Section 5. The Unified Future.
Tracing this evolution, we are officially leaving the post-hoc era of the past few years in the dust. April 2025 gave us the InternVL3 breakthrough. By August 2025, we'll see InternVL 3.5, which scales this exact recipe up with way more parameters and data. But the most incredible promise lies just over the horizon in 2026 with something called InternVL-U.
That U in InternVL-U stands for Unified Understanding and Generation. They are chasing a transfusion-style unified model. What that means in plain English is that the exact same native backbone that can flawlessly read text and understand images will also be able to natively generate and output original images too. It's no longer just an analyzer. It becomes a true multimedia creator, all operating from one single seamlessly integrated digital brain. I want to leave you with this to chew on. We've seen that native pre-training absolutely solves catastrophic forgetting, but it requires massive compute and incredibly scarce data. Does this mean the future of high-tier, natively trained OpenAI will be restricted to a few incredibly wealthy labs, effectively creating a new monopoly? Or is the friction of alignment debt so limiting that developers everywhere will have no choice but to pool their resources and just pay the steep price of native pre-training? It is a question that will absolutely define the next decade of artificial intelligence. Thanks for joining me for this explainer, and keep learning.